posted a zip file, not a folder called jar files in Canvas. So you should log in. If you log into a Canvas account, you should be able to see that. And inside that folder of jar files, you have 6 zip files. Okay. So you have to download it. I'll show you how to run them now. Okay. So
Java.
Jar.
Okay.
So you don't need, as long as you have Java installed on your computer, you should be able to run. Just install Java on your computer. Okay. So jar file is like an executable file in Java. Okay. So let me get started, and then when I have to show, I'll show that. Okay. All right. So this module is called Spectral Analysis. Okay. So it's basically trying to understand the characteristics of the graph. Okay. In the form of eigenvalues and eigenvectors. Okay. Have you heard of eigenvalues, eigenvectors? In math class. Alright, so the characteristics of a graph means how, say for example, the degree variation is there. Okay, so or if the graph is like all the edges between any two vertices, or the graph is sparsely connected, all these things. Okay, or the bipartite nature of a graph. So everything is captured in the form of eigenvalues and eigenvectors. Okay. Alright, so let me introduce you first to eigenvalues and eigenvectors. You're not going to see the computation from a math point of view, but I'm just going to illustrate with an example. So, given a matrix, a square matrix like this, not a square matrix is, right?
Was that symbol called?
Which symbol?
It is color.
Huh?
The second line.
This one?
Yeah, this one.
Lambda. So, what's the square matrix? Same number of rows and columns, right? So here you have 2 rows and 2 columns. So that's the square matrix. So this is a 2 by 2 matrix, right? So you're going to have 2 eigenvalues, and each eigenvalue will have a corresponding eigenvector. So what is the relationship involving the matrix is eigenvalue and eigenvector. So if you have a matrix A, okay, you can multiply that matrix with its eigenvector. Okay. The result of this multiplication will be a scalar. You know what a scalar is? A value, so 2.5 or just 3 or some scalar, some number, okay? Times the eigenvector. So the scalar is called the eigenvalue. So if they satisfy this relationship, then they are like the eigenvalue and the corresponding eigenvector. So for this given matrix, say 3, 2, 3 minus 2, of course there is a method that we can use to find the eigenvalues and eigenvectors for a matrix. We're not going to go through that method mathematically. We're going to use the jar file and the program I'm going to give you. But just to illustrate the property, 2, 1 is an eigenvector for this matrix. Okay, so vector means like just a column. Okay, and the corresponding eigenvalue is 4. So if I multiply, it's not a matrix or anything, it's just a scalar. So if I multiply these two, this is the eigenvector as a matrix. It's just like one column and all the rows are there. So it's a 2 by 2 matrix, that's a given matrix, and the eigenvector is a 2 by 1 matrix. So if you multiply these, you will get what? The eigenvalue multiplied by the eigenvector. So what is the right hand side? Right hand side is just multiplying each entry here with the scalar. So it's going to be 8 and 4. That's the right hand side. Now what is the left hand side? So to get the left hand side you have to do the multiplication. So let us do that. So this row multiplied by this column. So 3 times 2 plus 2 times 1 is 8, right? So that is 8. What is this second row? First column. So 3 times 2 plus negative 2 times 1 is going to be 4. So you see here the left hand side is 84, right? The left hand side is the same as the right hand side. Any question?
Sure. We can change the value like 4. We can change 4. Like we can put 5, 6, whatever.
If you put 5, 6, whatever, you should be able to find the corresponding eigenvector such that this property is satisfied. Is that clear? You cannot just come up with arbitrary value. So you are telling you can put this is like 5 times the eigenvector. So this is that matrix given to you 3, 2, 3, negative 2, right? So if you can find an eigenvector that satisfies this, yes.
So we need to check both sides. Then
This is just checking. Yeah, this is to illustrate. You don't have to really check. There are programs available to give you the answer, give you the eigenvalue and eigenvector. So since you guys see did not look like you have heard of this, I wanted to illustrate this problem. Yes, so you should have seen this. That's why I asked before. But at that time you were like, oh, I don't know what it is, right? So now you realize what it is. Okay. Any question on this property? So the number of eigenvalues and eigenvectors, again they are corresponding. So in this case, 4 is eigenvalue and 2, 1 is its corresponding eigenvector. So how many such eigenvalue, eigenvectors can you have for a matrix? So it depends on the dimension of the matrix. Here this is a 2 by 2 matrix, right? So which means you're going to have 2 eigenvalues and 2 corresponding eigenvectors. So if you have an n by n matrix, you're going to have n eigenvalues and each such eigenvalue will have the corresponding eigenvector.
Sir, is n times n or n x n matrix? I'm confused.
N times n by n matrix, that's how you say, right? This is number of rows and number of columns. That's a dimension, matrix. You haven't seen this anywhere so far? 2 by 2, 3 by 3, 2 by 4. If I say it's 2 by 4 matrix, it means 2 rows and 4 columns. Okay? Okay, so now if you look at again the definition of what spectral analysis is, trying to understand the characteristics of the network graph by doing what's called spectral decomposition in n dimensions. Okay, and how much you are able to get that for each dimension, for each direction is called like the extent to which you can do that is called the eigenvalue, and the corresponding vector is called the eigenvector. So what we are interested in basically is given a graph. So given a graph like this, we could use its adjacency matrix, okay, because the matrix here really corresponds to the adjacency matrix for us. So we can write the adjacency matrix for any graph and run through this program, and it will give you the eigenvalues and the eigenvectors. So this is a graph of what? 10 vertices. So it will have 10 by 10 adjacency matrix. So if you run the program, you're going to get 10 eigenvalues and the corresponding eigenvectors. So clear? Now the adjacency matrix, so unlike some arbitrary matrix like this which could have negative entries, the adjacency matrix of a graph is going to have only what? Positive entries, zeros or ones, right?
Can you repeat that again?
Any arbitrary matrix like this could have negative entries. But they are going to work with a graph, so it's going to have its adjacency matrix is always going to have positive entries, zeros or ones, or it could have some positive integers, that's fine. So it's not going to have negative integers. So when you work with a matrix that has no negative integers, only positive values, either zeros or positive values, could be even fraction, anything, not negative. Then the eigenvalues, all the eigenvalues are, well, I'll take it back 1 second. Okay, let me go back to tell one more thing before I tell the property. So I said you're going to have 10 eigenvalues, right? Now, among those 10 eigenvalues, the largest eigenvalue is guaranteed to be positive. Okay, so the 10 eigenvalues more likely to be different. Okay, now some eigenvalues could be the same, but the property is this: the largest eigenvalue among the eigenvalues for a graph is guaranteed to be positive if all the entries in the adjacency matrix are positive. Okay, so if you work with a graph, the largest eigenvalue is guaranteed to be positive because its adjacency matrix will have all entries positive, zeros or ones. Okay. Now, one more property. As I said, each eigenvalue has a corresponding eigenvector, right? So what I have shown here, let me blow it up a little bit. So these are the eigenvectors for each eigenvalue. So 3.3893 is an eigenvalue, like here out 4. Okay, so this is an eigenvalue, and this is the eigenvector because we have 10 vertices, we have 10 entries in the eigenvector. Okay, this 1.888 is another eigenvalue. This is its eigenvector. 1.1131 is another eigenvalue and its corresponding eigenvector. So like that you have 10 different eigenvalues, not different, sometimes some eigenvalues could be the same, but 10 eigenvalues. Okay, so 10 eigenvalues and each eigenvalue will have a corresponding eigenvector. Right here. Now, as I said, since the adjacency matrix is going to have only positive entries, zeros or ones or some positive values, the largest eigenvalue, so I have listed them with the decreasing order of eigenvalues. So this is the largest eigenvalue, 3.3893, 1.888 is the next largest, and then so on. So not only the largest eigenvalue is positive, all the entries in the corresponding eigenvector are also positive. Which eigenvector? The eigenvector corresponding to the largest eigenvalue. Is that clear? So there is a name for these two. The largest eigenvalue is called the principal eigenvalue. Okay? So the largest eigenvalue is called the principal eigenvalue, and the corresponding eigenvector is called the principal eigenvector.
So what are the use of this?
The whole module is on this, so you will get to know what is the use of all this. Okay, I'm just introducing eigenvalues, eigenvectors for now. Then we'll see the applications soon. So the largest eigenvalue is the principal eigenvalue, and the eigenvector corresponding to that eigenvalue is called the principal eigenvector. And what's the property? All the entries in the corresponding principal eigenvector are also going to be positive. You see the other eigenvectors, they could have some negative entries. Is that clear? Now, another property. It's all listed out there, okay? Now, the eigenvectors are orthogonal. You know what is orthogonal means? They are perpendicular. Okay, so a vector means like what? Some in one direction you have some line like x and y axis, they are perpendicular. and another direction, so these two are orthogonal. So we say two vectors are orthogonal when what? How do you decide whether two vectors are orthogonal?
They're perpendicular.
Yeah, so how you would say they are perpendicular mathematically?
90.
I've heard of this what is called dot product. Yes? So let me tell you based on the notation you might have seen. So this is say I plus j is a vector. Another vector, say I minus j. So dot product is something like this. So you multiply the corresponding coefficients of each dimension I and j. So it is 1i plus 1j dot product 1i minus 1j. Okay? So this is 1 times 1 for the I dimension plus 1 times negative 1 for the j dimension. So it's going to be 1 minus 1, which is 0. So if the dot product of two vectors is 0, we say they are orthogonal to each other. So now, if you take the dot product of two eigenvectors, any two eigenvectors, it's going to be 0. So how to take the dot product here? Multiply the corresponding entries. So 0.4741 multiplied say by, so I'm comparing these two vectors, the first two vectors. You could pick any two vectors. So 0.4741 multiplied with 0.0641 plus 0.4568 times 0.2043 plus 0.4453 times 0.2648 plus. So you keep on doing the multiplication and add them. You have some entries negative, so that will also contribute to the negative part. So that's why they add up to 0. Okay. So now you see why the other eigenvectors need to have some negative entries, because then only the dot product will become 0. Okay. Is that clear? So the eigenvectors are always orthogonal to each other. Okay. Any other properties for now? No. No, this thing. Alright, so I said this is a graph of 10 vertices. So the eigenvector is going to have 10 entries, right? And so, you know, when you write the adjacency matrix, how would you write it for this graph? You use the vertex ID as the row index and column index, right? So have the 10 vertices, 1, 2, 3, 4 up to 10, and then 1, 2, 3, 4 up to 10. So for 1, it has an H2 what? 2, 3, 4, and 5. So you have 1, 1 is 0, 1, 2 is 1. For 5 it is 1, but for 6, 7, 8, 9 there's no H, so it's all zeros, right? And then for 2, of course you see to which vertices it's connected, so it's connected to 1, 0 for 2 to 2, 2 to 3, yes, 2 to 4, 2 to 5, no, 6, 1, and so on. So you write this based on the vertex IDs, isn't it? So now, this is captured in the eigenvector. So the entries actually represent something about the vertices. Okay? We'll see more detail of this in the third module, but let me just introduce what they represent. So this entry corresponds, the first entry corresponds to vertex 1, the second entry corresponds to vertex 2 in each eigenvector. Okay, so in each eigenvector, the first entry corresponds to vertex 1, the second entry corresponds to vertex 2, and so on. Is that clear? Okay. Now, looking at the principal eigenvector, we know by now all the entries are going to be positive, right? The principal eigenvector. The entries in the principal eigenvector are called the eigenvector centrality of the vertices. So this 0.4741 is the eigenvector centrality of vertex 1. 0.4568 is the eigenvector centrality of vertex 2. 0.4453 is the eigenvector centrality of vertex 3 and so on. Now what does eigenvector centrality mean? We'll see more details later also. Now first of all, centrality of a vertex is like a quantitative way of referring to the importance of the vertex in the graph. Okay? So capturing the importance of a vertex in the graph in a quantitative way is called centrality. So it's called a centrality metric. Okay? The degree is a very basic centrality metric. So we can refer to degree as degree centrality. So how does it capture the importance of a vertex? The number of neighbors of a vertex, right? It's a measure of importance. If a vertex has more neighbors, it's probably more important for the graph because it has several neighbors. So like that, eigenvector centrality also captures the importance of a vertex. Okay, so it's called topological importance. Why it's called topological importance? Topology means how the vertices are connected to each other. Okay, so if more vertices are connected to that vertex, it has a higher importance. It is with degree centrality as well as with eigenvector centrality. Now let us see the difference between the two. Degree centrality is nothing but just the number of neighbors for a vertex. Now eigenvector centrality of a vertex is a measure of the degree of that vertex as well as the degree of its neighbors. Okay, so let us go back to this graph. So again, let me repeat the definition. Eigenvector centrality of a vertex is a measure of the degree of the vertex as well as the degree of its neighbors. So let us pick two vertices. Now, let us pick vertex 1 and 5. Between 1 and 5, which vertex has more neighbors? 5, right? So the degree of 5 is more than the degree of 1, right? But in terms of the eigenvector centrality values here, looking at the numbers here, the eigenvector centrality of 1 is 0.4741, and eigenvector centrality of 5 is 0.2986. Again, the entries need not be sorted. It just happens for this example problems like sorted. The entries really correspond to the corresponding vertices. Okay. Now, why you think the eigenvector centrality of 5 is actually lower than that of 1, even though it has a larger degree than 1? What's the definition of eigenvector centrality of a vertex? It's a measure of the degree of the vertex as well as the degree of its neighbors. So degree of 5 might be larger than the degree of 1, but look at the neighbors of 5 and the neighbors of 1. The neighbors of 1 are like what? 5 of course, then 2, 3 and 4. 2 has degree 4, 4 degree 3, 3 also has degree 4. So it's not only 1 has a reasonably larger degree of 4, all its 4 neighbors, of course 5 also has a larger degree, right? So I am having more neighbors and my neighbors are also having more neighbors. So it's a measure of like the density of the neighborhood. My neighbors as well as myself. Okay?
Yeah, it's like one person, one strongest person and another weakest person, but having so many friends.
You are stronger, and your neighbors are also stronger.
Yeah, that's
Where's the weaker coming now?
No, like one is stronger in comparison, one is stronger, and you have so many friends, so you are too stronger. That's
right. Yeah, so they contribute to you. Okay, yes. On the other side, look at vertex 5. It has more neighbors. Degree of 5 is larger. But what about the neighbors? They have only one neighbor. So 9 is degree is 1, 10 degree is 1. Of course, 1 has degree 4, 6 has degree 2, 7 also has degree 2. So neighbors of 5 have lower degree. So this one number, again remember at the beginning of the class semester I said you try to quantify it as an index. So this numbers captures that. Okay. So you may wonder how to quantify this. This guy has more neighbors as well as the neighbors have more neighbors, but vertex 5, even though it has more neighbors, all the neighbors have lower degree. So how to quantify it? So with just one number. So this number quantifies that 0.4741 for vertex 1 and 0.2986 relatively. Okay? Clear? So like that you can get the eigenvector centrality for every vertex. Okay? Any questions so far? Alright, so just remember this. So go back and look at it in more detail, this model as well as the third module.
Sir, how we will get those values?
Okay, that's what I'm going to show. So the program I'm going to give you the jar file already implements the algorithm to find it. Okay, it's a very time-consuming algorithm. So already you have the code for that. Okay, I'm going to give you the code.
Okay, and what is that table?
Okay. Okay, so to that program you need to feed this graph information. Otherwise, how will the program will run and find out the eigenvector? So you will be given the graph. You have to feed the information about the graph either as adjacency matrix or the list of edges. So you can call it as adjacency list. So the information given here is nothing but the list of edges. Okay. So I would suggest to use this as the adjacency list of format as input to your program, unless you need to input only the matrix. So I'll tell you a case or one or two scenarios where you have to use a matrix as input rather than instead of adjacency list. Other than that, those two cases you could use the list as input for all the other applications. Alright, so how to get this list? Just write the vertices in increasing order. So the first vertex, so each is an edge in this graph. So you start with 1 and write all its neighbors. So 1 to 2, then 1, 3, 1, 4, 1, 5.
Nothing should be repeated.
Nothing should be repeated.
Yeah.
So you should not write 2, 1. Okay? So since it's undirected graph, just one representation is good enough. So no 2, 1, but you have 2 connected to 1, 2 connected to 3, 4, and 6. So always the second ID should be larger. So yes, they're clear. So the second ID should be larger, as well as the first ID should be increasing. Okay, just as a convention, just to avoid making mistake. Okay. So 2, 3, 2, 4, 2, 6, then 3, 4, 3, 8. Then 4 is connected to 2, 1, and 3, all are lower IDs. So which means you would have already represented those edges here above. Okay. So there's no new edge to be added for 4. Then 5 is connected to 6, 7, and 10. As well as to 9. So 5, 6, 7, 9, 10. Then 7 and 8. The 6 is not connected to anything of higher ID. Okay. Then 7 is connected to 8. Then 8 is connected to 3 and 7. So they are already captured. 9 is connected to 5, already captured somewhere. And 10 to 5 already captured somewhere. Okay. 10 to 5 is captured here. So that's the adjacency list. So you use that as an input to your program. So let me show you how to run that now. So if you open each zip file, you'll see a folder there. So I opened here the EVC underscore adjacency list.
So where is that folder?
We'll go to your Canvas account and first open the jar files folder. Click that, you'll see those 6 zip files.
Yeah.
So download the EVC underscore adjacency list zip file. You see the zip file by the name EVC underscore adjacency list. Okay. So if you unzip it, you will see a folder called EVC underscore adjacency list, same name. Okay. So copy that folder and put it anywhere in your computer. Okay.
So 2 files and one one is matrix and another is
Yeah,
list.
so I'll use the list. So
List.
remember I said you can use either a matrix or list as input. So the list means it will take the list as input. Okay, so we'll use the list unless we need to use a matrix. So put it somewhere in your local drive.
Yep. Now put on Java.
Okay, so copy that EEC underscore SSC list folder. Let me create a new version. Okay. So once you open that folder, EEC underscore SSC list, you'll have a list of files. So you need to, so don't need to run or don't do anything with Java file. So Java is actually the package name, Java for matrix multiplication, I think it is. So it's like another executable jar file that has all the the APIs and everything in it. Okay. So you need to just run the other executable, EVC underscore adjacency list. You see executable jar file there. So double click on that. Okay. When you double click on that, the file template
Sir, which one?
EEC underscore adjacency list. You see the executable jar file there. Once you double click, it will open up the dialog box, the file what you call the window, from which you can choose the file. Which file to choose? You have to type up this. So let me close it. You have to type this list information and store this in a text file. Okay. So I have given some sample text files there as adjacency list -1, -2, and -3. So those are some sample adjacency list for some other graph. For your given graph, we have to type the adjacency list. So I copy this and try to save this as a file and proceed.
So it's coming something else. When we exit, something coming.
Yeah, close that.
Yeah.
Okay, so let me first type this. So I have entered the adjacency list. So how we enter the adjacency list? Make sure there's space between the vertex IDs. 1 space 2 and 1 space 3 and so on. Okay. So once you enter this, make sure after the last line there's no blank line. So you should not go to the next line. So 7, 8 is the last line, right? So make sure you keep pressing the delete button after the 8 so that there's no new line added after 7, 8. Is that clear? So the adjacency list file, the way you should type the information is type all the edges, and after the last edge you should not press enter. If you press enter, a new line will be added. So you should not have any blank line like this. So this is the last line. So place the cursor at the end of that vertex 8 and keep pressing delete so that no new line is added. So now save this. Control S, save this as some name. So this is like the name you could give for the adjacency list. You already have like 3 files there, as I said. You could store this anywhere. Okay, so let us save this. So I just save it inside the folder. You could save the text file anywhere. So this is say graph1, any name, and make sure it has the .text extension. Okay, so it's a text file. So now double click the EVC underscore adjacency list. It will ask you to open the file that you want to analyze. So now go to that folder where you saved this file and try to load it up. So I have saved it under the same folder. So graph1.txt. So that's the name of the file I saved. So just highlight the file and click open. So the program is going to run behind and compute all the eigenvalues and eigenvectors and show you the answer. So this is the these are the 10 eigenvalues. It's just like since it pulls out from an array, the index is 0 to 9. Okay, and these are the corresponding eigenvectors. So this is the eigenvector for the largest eigenvalue, which is 3.389. Okay, and the next largest eigenvalue is corresponding eigenvector. So if you are interested, mostly you're interested in the largest eigenvalue and the corresponding eigenvector, but sometimes you'll use the other eigenvalues and eigenvectors also. So if you want, you can save all this result to a file. You don't have to run this every time you need to do something with this graph. So there's a save to file button that you can click and save all the results to a file. So you can save again anywhere you want and save it as a .text file. So go to that folder or wherever you want to store and say, give some name, results for the results graph 1, so that you can know what it is. Again, since it won't give you the .text extension, you have to explicitly type .txt for the file name. So it says as a text file. Is that clear? So now when you open the text file, you can always see the numbers. So let me show that so that we can see the numbers bigger size. Okay, so it has to be formatted. Okay, so these are the, let me open in some other editor.
What?
No, the text editor, Notepad doesn't, what do you call, present it line by line. So I'm trying to use, we have to use Word, you see. So if you use Notepad, it was not, what do you call that? Line, truncating a line or, no. Try to open the result in Notepad if you have saved it. Okay, so Word displays it line by line. Okay, all right. So it's called line wrapping. You know, Notepad was not doing the wrapping for me. All right. So you see here now, these are the 10 eigenvalues and the corresponding. So these are the 10 eigenvalues here. Is it readable? And so this is the eigenvector corresponding to the largest eigenvalue of 3.389. So that's the principal eigenvector. Okay. So the entries correspond to what I showed you in my slide. 0.4741 for vertex 1, 0.2986 for vertex 5. So you have the numbers for all the vertices. Is that clear? Any question? So go back and try if you don't have a computer here. What's that? You're not able to get it?
Our Mac is not supported.
Oh, Mac. You have Java installed?
Yeah, I just downloaded it right now, but every time I'm trying to open it, it says,
No, if you, Java is installed already on your Mac.
yes, sir. I
Yeah.
just downloaded it right now.
You installed right now. Did you completely install it or you missed any step? You don't have to set up the class path, but to make the installation complete, I suggest to set up the class path. You know how
Yeah.
this class path? You have to find out where the bin folder is, and in Windows you have to go to the environment variables and set, there's a class path variable already there, so you have to add that path. So otherwise I just watch some video on YouTube to see how to install Java in a Mac machine and make sure that you completely install
So
it.
you have already this video?
Huh?
You have
I
already?
have for Windows, I guess. It should be, I'm not sure, let me see, it should be in one of my undergraduate class websites.
So it's on YouTube.
Huh?
It's on YouTube.
YouTube, a lot of people will show how to do this. Okay, search in YouTube, but if you have Windows machine, there should be one of my earlier classes that should show you. things you should know as a computer scientist, how to install a program, right? An application. Alright. So once you download, try it out and let me know. Okay? Or you can also come to my office and we'll work it out. Any questions so far? So this module is entirely based on this program, okay? So you have to make sure you get it running so that you can answer the questions. Alright. So let us start looking at the applications. So the first thing is called spectral radius ratio for node degree. Okay, so what it does is basically captures the extent of variation in the degree of a graph. You know, if you are given some numbers and you want to find the variation in that list of numbers, what is the statistical measure you typically use so far? If you want to find the average, you would use mean, or you add all the numbers and divide by the number of numbers, right? Now, what is the other statistical measure you would use to find out the variation? Like how the numbers are different from each other. What statistical measure you would use? Like you have the degrees of the vertices, right? So you want to see how varying they are. You would use standard deviation. But standard deviation, the magnitude, the value of standard deviation depends on the numbers. So for example, if your degrees are like 10, 12, 20, 14, 15, 17 and so on, the standard deviation would also be like 4.5 or some large value because the numbers are themselves larger. But if the degrees are like 1, 2, 3, 2, 4, 3, 2, 1, 2 and so on, the standard deviation is going to be like 0.5 or 1.2, some smaller numbers because the magnitude of the actual numbers itself is smaller. So if I just tell you two different graphs with standard deviation like this, it's not you cannot compare the two graphs based on these two standard deviation values because just because they have a larger standard deviation value does not mean there's a larger variation in the node degree. Because the degree values themselves are larger, you are more likely to end up with a larger value for standard deviation. Is that clear? So a more accurate measure using which you could compare any two graphs of different number of nodes and different magnitude of degree values is the spectral radius ratio for node degree. So how to find it out? Very simple. We know already what's the principal eigenvalue, right? So what is principal eigenvalue for a graph? What is that? The largest among the eigenvalues, right? Now there is a very interesting property which somebody showed. This is the property. So what is this? K means degree. So the principal eigenvalue is always going to be less than or equal to the maximum degree for any vertex in the graph. Okay? And it is also greater than or equal to the average degree of all the vertices. And we know the average degree of the vertices in the graph is going to be greater than or equal to the minimum degree because minimum is always the minimum. So if you look at from this side, the minimum degree for any vertex in the graph is going to be less than or equal to the average degree of all the vertices, which is going to be less than or equal to our principal eigenvalue, and that's going to be less than or equal to the maximum degree of any vertex in the graph. So if we take the ratio of the principal eigenvalue, so by the way, the principal eigenvalue also has another name, it's called the spectral radius. Okay? Several names. So principal eigenvalue, the largest eigenvalue, also called the spectral radius. Okay. So if you take the ratio of the principal eigenvalue, which is the spectral radius, and the average degree, that is called the spectral radius ratio for node degree. Okay. So that's the spectral radius ratio for node degree. Now anyone can say what is the minimum possible value for this ratio? The ratio of principal eigenvalue and the average degree. It's going to be always what? Greater than or equal to what? Just look at this in relationship. Principal eigenvalue is always going to be greater than or equal to the average degree, right? So the ratio of principal eigenvalue to the average degree is always going to be greater than or equal to 1. Is that clear? So this ratio is always going to be greater than or equal to 1. Because the principal eigenvalue is going to be larger, greater than or equal to the average degree. Okay? It's going to be equal to the average degree, which means the ratio is equal to 1 if all vertices have the same degree. If all vertices have the same degree, there's no variation in the degree values, right? It could be any value. It could be like all vertices have degree of 20 or all vertices have degree of 2. Doesn't matter. They have the same degree. So in that case, the principal eigenvalue will be same as the average degree, which is same as the degree, because all vertices have the same degree. How can a graph look like if all vertices have the same degree? Example is this. This is a degree 2. So all vertices have degree 2. Such a graph is also called a regular graph. Regular graph means all vertices have the same degree. So it's called a k-regular graph if all vertices have degree k, which means in this case it's called a 2-regular graph. All vertices have degree 2. Is that clear? So for a regular graph, the ratio is going to be always 1, which means if there's no variation in the node degree, the minimum value for the ratio is 1. If you start having variation in node degree for any arbitrary graph like what we are working with, there is going to be variation, right? So farther this ratio from 1, larger the variation in node degree. Okay? So larger the variation in node degree, the farther away the principal eigenvalue is from the average degree. Is that clear? So that is how it captures the variation in node degree. Okay? So let me look at a small example and then we'll look at it further. So how to get the ratio, spectral radius ratio for node degree? Given a graph like this, you know now how to find the principal eigenvalue, right? Type the adjacency list, fill into that program, EVC underscore adjacency list, find the largest eigenvalue, that's the principal eigenvalue, 3.3893. You also know how to find the average degree. How? Just find the degree of the vertices, sum it up, and divide by the number of vertices, that's the average degree. Then find the ratio of principal eigenvalue, in this case 3.3893 divided by 2.8, the average degree is 1.21. So you see here it's greater than 1. So it has some variation in the degree, of course, right? Because all vertices don't have the same degree. Now you want to compare two graphs. I have another graph, just a small variation, modification. I added a few edges like 5, 9, 7, I think that's the edge I added, and then 6, 10. So I added a couple of edges and I removed this edge from 5, 1. Okay, and I added one more edge. So I did some small variation modification to this graph. And I do the same thing. This is now the adjacency list for this graph. I feed this information to the program. It gives me a principal eigenvalue of 3.4735. And the average degree changes a little bit because the degrees of the vertices changed. The average degree comes out to be 3.2. So the ratio is now 1.09. So you see now it is less than 1.21. So which means what? Between the two graphs, this graph has what? Less variation in node degree compared to this graph. Okay, and you quantified it how? The ratio for spectral radius ratio for node degree is 1.09 and 1.21. So the numbers also give you a feel. It's not like this is like 2.5 and this is 1.09. This is almost close to it, 1.21 and 1.09. So these numbers don't depend on the number of vertices. You could have a graph of 100 vertices, could still get the spectral radius ratio for node degree to be 1.21. you could have a graph of 10 vertices, you could get the spectral usage should be 1.09. So the number of vertices or the number of edges don't really matter. It's just the variation in the degree that is captured. So it's a very powerful measure. Okay, greater than or equal to 1, independent of the number of nodes and edges. Okay, so go back and try all these things and see you can proceed
Sir,
up to
can
this
you
point.
please tell the last sentence? You say like greater than.
It's always greater than or equal to 1, right? Because
Yeah.
the principal eigenvalue is greater than or equal to average degree. And it's independent of the number of nodes and edges. So as I said, you could have a graph of 100 vertices, you could still get something like 1.21.
Okay, got it.
Okay? So go back and try all these things before you come next class so that you can proceed. Okay?